Okay, so imagine this. You have to capture a perfect, pristine snapshot of a fluid. Sounds simple enough, right? Except this fluid is miles below the Earth's surface, under crushing pressure and at extreme temperatures. Yeah, we're not just talking about dipping a bucket in a well. This is a super high-stakes, incredibly precise operation where one tiny mistake can cost millions. So how do they actually pull it off? Let's break down the science and the insane precision required. Here's the plan. We're going to follow the entire journey of this one sample. First, we'll get into why this is such a high-stakes game. Then, we'll walk through how they meticulously prepare the well. After that, we'll see the sampling itself in action, learn how scientists prove they got it right, and even dig into the strange mystery of a vanishing gas.
So let's really set the stage. We're talking about grabbing a sample from a reservoir deep inside the Earth. And this isn't just any old fluid. It's a complex mix of liquids and dissolved gases. The properties of this fluid, well, they're the foundation for massive, multi-million-dollar engineering and financial decisions. No pressure, right?
And that brings us to the big question, the central challenge of this whole thing. How on earth do you grab a sample from way down there, bring it all the way back to the surface, and make sure it hasn't changed one bit? How do you guarantee that what you're testing in a sterile lab is exactly what exists miles underground? It is a monumental challenge of pure precision.
Before you can even think about sending a tool down hole, you have to prepare the well itself. Now, this isn't just about cleaning things up. It's about creating the perfect, stable conditions for a perfect sample. Get this part wrong, and seriously, the entire mission is compromised right from the get-go.
This prep process has 3 absolutely critical steps. First, the well is conditioned. Think of it like letting a shaken-up soda bottle settle down. You have to ensure all the gas is properly dissolved into the liquid, creating one uniform single-phase fluid. Any rogue bubbles would completely ruin the sample. Next, a full pressure and temperature survey maps out the entire environment. And maybe most importantly, these conditions are monitored in real time. You have to be absolutely certain that the environment is perfectly stable at the exact moment you take that sample.
All right, with the well prepped and stable, it's time for the main event, the operation itself. This is where mechanical precision meets geology. A specialized sampler tool begins its long journey down to the target depth. The level of detail here is just incredible. The tool isn't just dropped down there, nope. It's lowered at a very specific controlled speed to avoid stirring up the fluid and changing the pressure. Then, it's positioned with pinpoint accuracy right where the reservoir fluid enters the well. The tool's sample chamber is then flushed over and over again, making sure only fresh, authentic reservoir fluid is what gets trapped inside. Every single step is meticulously choreographed, sometimes even timed down to the minute. And get this, you don't just do all that work once. The protocol demands a minimum of 3 separate samples. So why 3? It's all about redundancy and verification. Later, back in the lab, the results from these samples are all going to be compared against each other. It's the ultimate cross-check to make sure you've actually captured the truth.
So, the samples are finally back on the surface. Phew, journey's over. The hard part's done, right? Not even close. Now comes the real moment of truth. After all that work, you have to prove that what you're holding in your hands is a valid, truly representative sample. The key test for this measures something called the bubble point pressure. Put simply, it's the exact pressure where dissolved gas starts to escape the liquid. It's the fizz you see when you crack open a soda. This specific pressure value acts like a unique fingerprint for that reservoir fluid. And here is where that trio of samples becomes so important. The bubble point measured for each sample has to match the others within an incredibly tight window, just 2%. If they're off by any more than that, it means something went wrong, and all those expensive samples are invalid.
But there's a fascinating little catch in the measurement process itself. You can have 3 perfect samples, but if you make one simple procedural error back in the lab, you can get it all wrong. So what is that one tiny mistake?
The mistake is, well, it's shockingly simple. Not agitating the sample. To get an accurate reading, the lab technician has to physically rock the sample container as they change the pressure. Without that simple motion, the gas bubbles just don't form correctly, and that can lead to a measurement error of up to 50%. A tiny physical action is literally the difference between a perfect measurement and a completely useless one.
Okay, so let's say you've done everything right. You've got 3 perfect samples, and they've all passed the validation test with flying colors. You're home free. But there's one last ghost in the machine you have to account for, the vanishing gas problem.
The problem lies with these notoriously tricky compounds like hydrogen sulfide, or H2S.
In the time it takes to get the sample from the well all the way to a lab, that H2S can literally just vanish. It can react with the container or get absorbed into the fluid. The result? The lab will report a lower concentration than what's actually in the reservoir. So the only solution is to analyze for it right there, on site, immediately after it's collected, before it gets a chance to disappear.
So if we boil this entire complex process down, it's really a story told in 4 parts. The preparation has to be absolutely perfect. The execution requires robotic, flawless precision. The validation process is strict and completely non-negotiable. And finally, you have to account for those hidden variables, like the vanishing gases, that can fool you even at the very last step.
And this is why it all matters so much. This isn't just an academic exercise. A perfect sample is the bedrock, it's the foundation upon which multi-million-dollar decisions about how to develop an entire energy resource are built. The data from this single, tiny volume of fluid informs these massive investments.
It really leaves you with a final thought, doesn't it? This whole process reveals just how much incredible effort goes into ensuring data is true and reliable. It makes you wonder, what other invisible challenges, maybe in medicine or space exploration or material science, demand this same extraordinary, almost obsessive level of precision just to get the right answer?